These examples go with Lesson 2.1, Quadratic Functions and Applications. Example 1. Given the function g of x is equal to the quantity x plus 2 squared minus 1, part A, determine whether the graph of the parabola opens up or down. When your function is in vertex form, determining whether the graph is going to open up or down is going to depend entirely on whatever number is out here being multiplied by the parentheses. Now in this case, there is an understood 1 out here, and since this 1 is a positive 1, and we know that because there was no negative here, that means that this one is actually going to open in the upward direction. If this number out here were negative, then we would know it would open in the downward direction. Part B, identify the vertex. Well, the vertex is located at H and K. And H, we want the opposite of this number, and then K is going to be back here. So the vertex is going to be at -2 and -1. And let's go ahead and graph that right here, because we're going to have to graph this down in part E. All right, part C, determine the x-intercepts. Well, the x-intercepts are the numbers you get when y is equal to 0. So we're going to take our function here. We're going to put 0 in instead of g of x, and we're going to set it equal to x plus 2 squared minus 1. And I am going to add 1 to both sides here. And this is going to give me 1 equal to x plus 2 squared. And then to eliminate the square, I am going to square root both sides. And don't forget, we want the plus minus out here. And then the square and the square root will cancel. So on the left, we're going to be left with x plus 2. And on the right, we're going to be left with x plus 2. On the left, the square root of 1 is 1. So we're going to have plus or minus 1 over here. And then let's subtract 2 so that we can get x all by itself. That gives me -2 plus or minus 1 equal to x. If -2 plus 1 is equal to x, then x is equal to -1. That's an x-intercept. And we can plot it right here at the point -1, 0. If -2 minus 1 is equal to x, then x is going to be equal to -3. There's my other x-intercept, and I can plot that one right here. Okay, so for part C, the x-intercepts are at -1, 0 and -3, 0. D. Now we have to find the y-intercept. Well, the y-intercept we can find when x is equal to 0. So I'm going to take and put 0 in for x. Let me make a little bit of room here so we can do some work. Okay. Alright, and I am going to put 0 in for x this time, and we're going to be solving for y, or g of x. I'm just going to put a y in place of the g of x. So y is equal to 0 plus 2 squared minus 1. Well, 0 plus 2 is just going to be 2, so we've got 2 squared minus 1. 2 squared is 4, and 4 minus 1 is going to be 3. So that means we have a y-intercept right here at 3. The y-intercept is located at the point 0, positive 3. All right, part E, sketch the function. Well, we've got most of it right here. We can just connect our dots into the parabola like so. All right, part F, determine the axis of symmetry. The axis of symmetry goes through the vertex. It is a vertical line that's going to go through the vertex. And since my vertex is right here, the axis of symmetry is going to be the imaginary line that goes straight through there, just like this. And the equation of this line is x is equal to -2. G, determine the maximum or the minimum value of g. This function is going to have a minimum value, and I know that because the parabola opens up in the upward direction. There's no graph down here below. We do have a lowest point, and that lowest point is -1. Remember, we talked about max and min. Where the maximum or the minimum happens is the x-coordinate, but what the maximum or the minimum is going to be the y-coordinate. And since the coordinates of this point right here, the vertex, are -2 and -1, the minimum is going to be at -1, the y-coordinate. Okay, the domain and the range. Well, the domain we've been working on for a while. When we take a look at the original function, remember our rule. The domain of any function is all real numbers unless you're dividing by a variable, which we're not, or there's a square root somewhere in the problem. And again, there's not. So our domain is going to be all real numbers from -infinity to +infinity. All right, now the range. This is asking about the y values. So this is up and down. So we're going to go from the lowest point on the graph to the highest point on the graph. Well, the lowest this graph can go, we've already said, is -1. And since there's a closed circle right here, we know that's going to be included in the range. Now for the highest point, we're going to follow the graph. And look, I have arrows on both sides here indicating that this is going to move up and to the right forever. This one's going to move up and to the left forever. That looks like it's going off to +infinity. So the range is going to go from -1 with the bracket to +infinity. Example 2. Given the function f of x is equal to 3x squared minus 6x plus 1, part A, write the function in vertex form. Well, there's a couple of ways we can get the vertex for the parabola if it's not already in vertex form. And one of them is by the process of completing the square, because doing this, not only can we find the vertex, but we can actually have the parabola in its form to graph everything pretty easily, because in vertex form we can pull out the vertex, we can tell if it opens up or down, we can get to the x and y intercepts pretty quickly. So we'll go through the process and we're going to complete the square. The first thing I'm going to do is I'm going to take that f of x out and I'm going to replace it with a y. So we have y is equal to 3x squared minus 6x plus 1. Okay, to complete the square, I'm going to isolate the two terms that have a variable with them. So I'm actually going to subtract this one over here to the other side. And I'm going to bring it back afterwards at the very end. But for now, we're going to put it over here so I don't have to worry with it. All right, so now we have 3 times x squared minus 6x, and this is equal to y minus 1. Okay, the next thing that I need to do is this number right here on my x squared has to be a 1, and it's not. Okay, so I'm actually going to factor that out. So we have y minus 1 equal to 3 times x squared minus 2x. All right, the process for completing the square has me looking right here at my b term. This is the one that has the linear variable on it. And I'm supposed to take half of that number and square it and add it to both sides. So let's see. We'll come out here for a second. We're going to take -2. We're going to divide it in half. And then whatever I get, I want to square it. So let's see. -2 divided by 2 is -1. -1 squared is going to give me a +1. And so the parentheses here, this is going to be 3 times x squared minus 2x plus 1. Now, we can't just add 1 over here to this side. We have to add 1 over here as well because of the equality sign. But the thing is, I don't want to add 1. Remember, I factored that 3 out there. And if I distribute the 3 back into the parentheses, we're going to get 3x squared minus 6x plus 3. So instead of adding 1 to both sides, I'm actually adding 3 to both sides. Okay, let's simplify. -1 plus 3, that's going to give me a 2. Over here on the other side, remember, this is going to factor. We've set this up on purpose so that it will factor. And it will factor in x minus 1 times x minus 1, which we can write in shortened version as x minus 1 squared. All right, and then to get this into vertex form, I'm supposed to solve for y, so we'll just subtract 2 from both sides. No like terms in here, so y is going to be equal to 3 times the quantity x minus 1 squared minus 2. And now I can just convert that back into function form by replacing the y with an f of x. So let's put that up here. F of x is equal to 3 times the quantity x minus 1 squared minus 1. Okay, now I'm going to clean all this up over here so we can do a little bit of work and finish the rest of the problems. Okay, part A is already done, and we have figured out the function in vertex form. Now for part B, we're supposed to identify the vertex. So remember, that's h and k, and that's going to be the opposite of this number right here, and then this number right here. So the opposite of -1 is +1, and then back here we have a -1. That means my vertex is going to be located right here, +1 and -1. Okay, x-intercepts. Remember, to find the x-intercepts, we're supposed to put 0 in for y and then solve for x. All right, so our equation is going to be 0 equals 3 times the quantity x minus 1 squared minus 1. Let's add 1 to both sides here. That gives me 1 equal to 3 times the quantity x minus 1 squared. All right, let's divide both sides by that 3 there. 1/3 equal to x minus 1 squared. And then to solve this, we're going to unsquare by taking the square root of both sides. Don't forget the plus minus. This is going to give me x minus 1 squared. Of course, they're going to cancel out, so we're going to be left with plus or minus. Now, 1 has a nice square root. It's just 1. But the square root of 3, not so much. And then over here, we've got x minus 1. Let's add 1. All right, so we have x is equal to 1 minus, plus or minus, 1 over the square root of 3. If x is equal to 1 plus 1 over the square root of 3, then in the calculator, that's going to give me about 1.6 if I round it off to the 10th place. All right, if we do x is equal to 1 minus 1 over the square root of 3 in the calculator, that is going to give me about 0.4 if I round it to the 10th place. So 1.6 is going to be right here in between 1 and 2. 0.4 is going to be right here in between 0 and 1. All right, part D. Now we want to find the y-intercept. The y-intercept we can find by substituting in 0 for x. We have y is equal to 3 times 0 minus 1 squared minus 1. 0 minus 1 is just -1, so we have 3 times -1 squared minus 1. -1 squared is +1, so we have y equal to 3 times +1 minus 1. And then 3 times 1 is 3, so y is equal to 3 minus 1, which means that y is equal to 2. And that puts my y-intercept right here at 0, 2. And let's see, my x-intercepts were at 1.6 and 0 and 0.4 and 0. All right, part E, sketch the function. Well, we can do that pretty easily. We've got our dots in here. We'll come down here, turn around, and move back up in that direction. And there's our parabola. Okay, F, the axis of symmetry. Remember, the axis of symmetry goes through the vertex. The vertex is right here. This is our imaginary line. cuts the parabola exactly down the middle through its vertex, and the equation for this line is x equals 1. The maximum or minimum, we're down here at part G. This one is going to have a minimum, and I know that because our parabola is opening up, and the minimum is right here at the vertex because there's no graph below it. And remember, the minimum is the y value of this point right here, and the y value of this point is -1. All right, write the domain and the range. The domain, again, we're not dividing by any variables here in the problem. We don't have any square roots anywhere here in the problem, so the domain is going to go from -infinity to +infinity. The range is going to take a little bit more work. Remember, we're going from low to high. The lowest point on this graph is right here. We've already said that's -1, and it does have a closed circle there, so we're going to put a bracket on it. The high point, well, I've got an arrow on this side, I've got an arrow on this side, so it looks like both of these are heading off toward +infinity. Example 3. Given the function f of x is equal to -x squared minus 4x minus 7, part A, state where the parabola of the graph opens up or down. Sorry, the graph of the parabola. Okay, in order to figure that out, we're going to look at our x squared term, our leading term right here. Since it's negative, that tells me that this one is actually going to open in a down direction. If it were positive, then we would know that this one would open up. Okay, now B is asking for the vertex. We can actually use the shortcut to find the vertex because this problem doesn't ask me to put the original function into vertex form. So the x-coordinate for the vertex is going to be the opposite of B divided by 2a. Okay, so A is -1, B is going to be -4, and of course C is going to be -7. So the x-coordinate for the vertex is going to be the opposite of -4 divided by 2 times -1. Two negatives make a positive, that's going to give us 4. 2 times -1 is -2, and 4 divided by -2 is -2. So the x-coordinate for the vertex is -2. Now your textbook gives you a formula to try and figure out what the y-coordinate is, and then they tell you a little secret about how it might be a little bit easier if we just take this number we found for x and plug it into our original problem and see what y is going to be, because that'll give us the vertex too. Alright, so let's see. To find the y-coordinate, we're going to substitute in -2 for x, so we have the opposite of -2 squared, minus 4 times -2 minus 7. -2 squared is +4, so we've got the opposite of 4. -4 times -2 is going to give us +8, and then minus 7. Let's see, -4 plus 8 is +4. +4 minus 7 is going to give us -3, so it looks like our vertex is going to be at -2 and -3. And we can actually go ahead and plot that in here. And we know it's going to be opening down. Okay, let's clean a little bit of this off because for part C we have to find the x-intercepts. Okay, to find the x-intercepts, we can, let's see, we set this equal to 0. So our equation is going to be 0 equals -x squared minus 4x minus 7. I can actually divide everything here by -1 so that I have a positive x squared there. I don't have to, but I'd rather have a positive leading term there. Alright, so we got x squared plus 4x plus 7. Now in a case like this, we would normally want to factor this. That might be the quickest way to figure out what the x-intercepts are, but there aren't any factors of 7 that will add together and give me 4. And that means I have to use my quadratic equation. So we're going to use a equal to 1, b equal to 4, and c equal to 7. And our x-intercepts are going to be the opposite of b plus or minus the square root of b squared minus 4 times a times c and all of this gets divided by 2a. All right, so we have -4 plus or minus the square root of, let's see, 4 squared is 16, 4 times 1 is 4, 4 times 7 is 28. We've got 16 minus 28. That's going to give me -12, and this is over 2. And I really don't have to go any further because I have this negative right here underneath the radical, and that causes a problem. That means we have imaginary x-intercepts. Now really this shouldn't surprise us because we knew back here in part A that this parabola was going to open down, and then my vertex ended up being down here below the x-axis, which means it's going to be opening in this direction right here away from the x-axis. And what that tells me is, since it's opening down, it's never going to intersect my x-axis here. Alright, let's go on to part D and get the y-intercept. To get the y-intercept, we want to put 0 in for x, and then we're going to solve this for y. So we're going to have the opposite of 0 squared minus 4 times 0 minus 7. Well, this we know is just going to cancel out. It's going to be 0. This we know is going to cancel out. It's just going to be 0. So it looks like my y-intercept is going to be at -7. And that's going to be right here. And we had no x-intercepts there. Now, E is asking us to sketch the graph, and we really only have 2 points here to sketch the graph. And so it's going to be a little bit tricky to try and do this with just 2 points in it. But we can use the fact that these parabolas are symmetric. So let's go ahead and move on to F and find the axis of symmetry. We said that -2, -3 right here was going to be the vertex. And remember, the axis of symmetry is just an imaginary vertical line that goes through the vertex of a parabola. Okay, what this tells me, and by the way, the equation for this line is going to be x is equal to -2. Every point that's over here on this side of the parabola has to be reflected over here on this side of the parabola. So we're going to use a trick from our transformations. Since I know that this point is 2 boxes away from the axis of symmetry, there must be a point that is also 2 boxes away from the axis of symmetry on this side, which means we should have a point right here. And now I can see I have 3 points in here, and I can get a definite sketch for my curve. Part G, determine the maximum or the minimum. This graph is going to have a maximum, and I know that because the graph opens down. Here's my vertex. There is no graph up above it. The maximum value occurs at the y-coordinate of this point, and that's going to be -3. For H, we want the domain and the range. Well, the domain, have you figured it out yet for all of these, is going to be -infinity to +infinity as long as my graphs are opening up and down, and for our intents and purposes, they will be. So the range is where you're really going to have to be doing your work. And remember, you're going from the lowest point to the highest point. Now be careful here. The vertex is not the lowest point this time. It was a maximum. It is the highest point. The lowest point this graph can go, well, we've got an arrow right here. We've got an arrow right here, meaning that both of these are heading down toward -infinity. And then the highest that it can go is right here to the vertex, where we said y was equal to -3. And because of that closed circle, we do want to put a bracket on it. Okay, example 4. A quarterback throws a football with an initial velocity of 72 feet per second at an angle of 25 degrees. The height of the ball can be modeled by the function h of t is equal to -16t squared plus 30.4t plus 5, where h of t is the height in feet and t is the time in seconds after release. Part A. Determine the time at which the ball will be at its maximum height. Okay. This problem is giving us the key word right here, maximum. We already know this is going to be a parabola. The highest exponent here is 2. And we know it's going to be opening down. And the maximum actually occurs at the vertex. So this part A problem is asking us to find the vertex. And specifically, because it's asking for the time, and time t is our independent variable, it's asking us to find the x-coordinate of our vertex. And we can do this by using the little shortcut of the negative b divided by 2a. All right, so let's see. A is going to be negative 16, B is 30.4, and C is going to be positive 5, so the time is going to be the opposite of B divided by 2 times A. And let's put that in the calculator and see what we get. And that's going to give me 0.95. And our units on this is going to be seconds right there. Okay, so for part A, 0.95 seconds. All right, part B, determine the maximum height of the ball. And again, there's a key word, which tells me, again, we're going to be dealing with the vertex. And since we've already found the x-coordinate, now it's asking me what the maximum is. Well, that's the y-coordinate of the vertex. So now that we have x, we'll just plug it into our original problem and see what we get back for y. Okay, so h of 0.95, this is my y, is going to be equal to negative 16 times 0.95 squared plus 30.4 times 0.95 plus 5. And I am going to put all of this into my calculator and see what I get back. And that gives me 19.44. So for part B, the maximum height is 19.44, and let's see, our units are in feet here. So 19.44 feet. Okay, C, determine the amount of time required for the ball to reach the receiver's hand if the receiver catches the ball at a point 3 feet off the ground. Okay, so the 3 feet right here, this is important. This is a height. And so what we want to do is we're going to solve our original equation when it's equal to 3. So we're going to have negative 16 t squared plus 30.4 t plus 5 equal to 3. And in order to solve this, it needs to be equal to 0. So let's subtract the 3 from both sides. That gives us negative 16 t squared plus 30.4 t plus 2 equal to 0. And now we can put this in our quadratic formula, but I'm going to need to clean this up a little bit so we have. All right, so let's see, we'll have A equal to negative 16, B equal to 30.4, and C equal to 2. All right, that means we're going to have the opposite of B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. Okay, this is going to give me negative 30.4 plus or minus. All right, let's put that radical in the calculator and see what we get. And this is going to give me 1052.16. And we are supposed to be square rooting this still. And on the bottom, we've got negative 32. Okay. We got negative 30.4 plus or minus. Now, let's square root this and round it off to 1 decimal place. And that's going to give me 32.4. And again, this is divided by negative 32. So we can have negative 30.4 plus 32.4 divided by negative 32. Let's see what that gives us. That gives me negative 0.0625. Now, since the t stands for time and we've got a negative number here, we can throw that one out because our time can't be negative. All right, let's try our other one. We can also have negative 30 minus 32.4 divided by negative 32. Okay, let's put that into the calculator and see what we get. And that's going to give me 1.95. And remember, our time here is going to be in seconds. So it takes almost 2 seconds for the receiver to catch the ball about 3 feet off the ground. Example 5. A farmer has 200 feet of fencing and wants to build 3 adjacent rectangular corrals. Determine the dimensions that should be used to maximize the area and find the area of each individual corral. All right, let's draw a picture of this. We know farmer wants to make a corral that is separated into 3 pieces like this. So adjacent would mean that they're touching and they're all going to be rectangles. Okay, and he's got 200 feet of fencing all together, so each side is going to represent part of that 200 feet. Okay, so let's see. We can call this side right here a length, and we can call this side right here a width. The first thing I know is that if we add 2 lengths plus 3 widths, that should give me all of the fencing that I have to use. Because there's a length, there's 1. Here's another length down here on this side. That's where I get my 2 lengths. And then my widths. There's 1 here, 1 here, 1 here, and 1 here. So that should be 4 widths instead of 3 widths. Sorry. Let's change that. We have 4 widths. The other thing that I know is that the area for a rectangle is going to be the length times the width. So we're going to get the area of the giant rectangle out here, and that's going to be 1 length times 1 width right here. Okay, so we want to maximize the area. And maximizing the area means we're going to need to find the vertex of a quadratic function, which I don't currently have, but I'll have one in just a second. Because what I'm going to do is I'm going to solve this equation up here for L. And then whatever I get, I'm going to substitute down here into this L. And that's going to give me a quadratic equation down here where I can find the vertex of. Okay, so let's see. Everything is even. So let's divide everything by 2. Actually, let's subtract the 4w over to the other side first. All right, these are not like terms. So you have 2L equal to negative 4W plus 200. And now to get L alone, we will divide everything by 2. So L is equal to negative 2W plus 100. All right, and I'm going to take this right here, and I'm going to plug it into my area formula. And that's going to give me, for L, okay, that's going to give me negative 2W plus 100 times W. And let's go ahead and distribute the W into the parentheses. That gives us negative 2W squared plus 100. Okay? All right, now we're going to try and figure out the vertex of this so we can get to the maximum, because here's my key word right here. And we know it's going to be a vertex, and we know it's going to be a maximum because we have a -2 right here, so we know this thing is going to be opening down. Okay, so let's see. A is going to be equal to -2. B is going to be 0 because there is no w to the first power. And C is going to be equal to 100. Wait, let's try this again. When we distribute that w in there, 100 times w is going to give me 100w. So B is going to be 100. C is going to be equal to 0 because there's no constant term back here. Okay, let's see. So the x-coordinate of the vertex is going to be -100 divided by 2 times -2. So this is going to be -100 divided by -4, which is going to give me 25. And I probably should have put a w here instead of an x. All right, and then to get to the length, we can just plug in our 25. Oh, this is really off. Sorry, this is 25. We can plug our 25 back into the formula right here, and it should tell me what the length is. So let's see. 2L plus 4 times 25 is 200. And we know that 4 times 25 is 100. So we'll subtract the 100. We've got 2L equal to 100, which means that L is equal to 50. Okay, now let's go back and look at our picture. Oops. We know that L right here is equal to 50, so that's this entire side right here. And we know that W is equal to 25, and that's going to be this entire side right here. And we are supposed to find the dimensions used to maximize the area. Well, this is the vertex, so that's going to maximize the area. And now we're going to find the area of each individual corral. So this one, and this one. Now remember, they're supposed to be exactly the same. So there's a couple of options we can do. If we find the area of this outer blue rectangle here, that'll give me the area of all 3 of these together. And then since they're exactly the same, if I divide that by 3, it will give me the area of each individual corral. All right, so the area is going to be 50 times 25. That's going to give me 1,250 square feet. And then the individual areas is going to be 1,250 divided by 3. And that's going to give me 416.67 square feet. Example 6. The funding F of T in millions of dollars for a drug rehabilitation center is given in the table for selected years T. A. Use regression to find a quadratic function to model the data. So we're going to need to pull up Desmos to help us with this, because Desmos is going to give us our quadratic regression equation. All right, you can see over here on the side, I've already entered in the data from our box in the previous problem. And I'm going to shrink this just a little bit so we can actually see all of our points. And there they are. And you can see they kind of do go in a parabola shape. These two being right here side by side, there's a good chance the vertex is somewhere in between these two, just a little bit lower. Okay, to figure out what our regression equation is going to be, we're going to put in y is approximately equal to, and actually this should be y1, approximately equal to a times x1, and that's going to have to be squared. All right, plus B times x1, and then plus C. Alright, so what this does for me is putting the 1 subscripts on here is telling Desmos to use my table up here, because you'll notice it's x1 and y1, it's not just x and y. And then the squiggle part here, this little tilde, tells Desmos to figure out what the equation is going to be. Now remember, the parameters down here in the bottom of the box, this is exactly what I need right here. There's my A, here's my B, here's my C, there's my equation. I just need to plug them into the right places. Okay, so now I'm going to take this over to the PowerPoint, and we're going to fill in our equation, and we'll have part A complete. And I think I'm going to round these to 3 decimal places. Alright, so here's my equation as I translated it over from the Desmos screen. We have y equal to 0.060x squared minus 0.593x plus 3.486. For part B, during what year is the funding the least? Okay, and we're going to round it to the nearest year. Well, our key word here is least. That's telling me that we are looking for the vertex. And we know that it's going to be a least or a minimum because my A coordinate, my A sign here is positive. So this means this parabola is going to be opening up. And we did see the picture of the points, and we knew that it was opening up. Okay, so the funding is going to be the least during what year? We're going to use 0.060 for A. We're going to use negative 0.593 for B, and we're going to use 3.486 for C. So T is equal to the opposite of B divided by 2 times A. Another 0 in there. Alright, and let's put this in the calculator and see what we get. And this is giving me 4.942, but if we round this to the nearest year, we're going to be rounding it up. So 5 years. It looks like during year 5, the funding received the least amount, or the drug rehabilitation center received the least amount of funding. Then see, what is the minimum yearly amount of funding received? We're going to round this to the nearest $1 million. Okay, this is going to be a matter of finding the y coordinate for the vertex. We found the x coordinate. Now all we need to do is plug this number 5 into our equation here and see what we get back. So y is going to be equal to 0.060 times 5 squared minus 0.593 times 5 plus 3.486. And let's put that in our calculator and see what we get. And this is giving me 2.021, and if I round this to the nearest $1 million, it looks like $2 million is going to be the least amount that this drug rehabilitation center has received.